In the previous video, we looked at the following three-step mechanism. That three-step mechanism gives rise to the overall equation of Cl2 gas plus CHCl3 gas in equilibrium with HCl gas plus CCl4 gas. We were told that the second step of this elementary mechanism was the slow step, so that means the rate law is going to be determined by that step. This gives a rate equal K times Cl times the concentration of CHCl3. But this is not the right answer because Cl is an intermediate, and we need this rate law expressed in terms of Cl2. So we have to introduce a concept called the steady state approximation. And the steady state approximation is going to allow us to express the overall rate law in terms of Cl2 and not the intermediate Cl. So when you use the steady state approximation, you must solve for the concentration of the intermediate by assuming that an equilibrium is established in the fast step which precedes the slowest step. Okay, so what do we mean by this? So if we look, the mechanism that precedes our slow step is actually a fast step right here, and it's an equilibrium between Cl2 gas and 2Cl. So let's analyze this equilibrium expression. We have Cl2 gas in equilibrium with 2Cl gas. Remember, an equilibrium is going to have a constant of K1 for the forward reaction and K to the minus 1 for our reverse reaction. So we can kind of break this down into two parts. The first part is going to be the rate of Cl2 decomposition. And that is going to be rate is going to equal K1 times the concentration of Cl2. Because the Cl2 decomposition is the Cl2 breaking down into the Cl. On the flip side, we can look at the rate of Cl formation. And that is going to be, the rate of the Cl2 formation, which means we're going to have 2Cl going over to Cl2, or this reverse reaction here. That rate is going to be equal to K to the minus 1 times the concentration of Cl, that quantity, squared. So if we assume this equilibrium is established, that means the rate of the forward reaction, which is the Cl2 decomposition, has to be equal to the rate of the Cl2 formation. So we can set these two equal to each other. That means K1 times Cl2 is going to equal K minus 1 times Cl, that quantity, squared. And here we need to solve for Cl and hope that we can solve for that in terms of Cl2. So our concentration of Cl squared is going to equal K1 divided by K minus 1 times the concentration of Cl2. If we take the square root of all this, that's going to give us the concentration of Cl, and that's going to equal the square root of this entire thing right here. If we take the square root of a constant, it's still a constant. So we're just going to write this as K times the concentration of Cl2 to the 1/2 power. All right? So now we can say that this expression right here can be plugged back in to our overall rate, because our overall rate from what we calculated earlier was that the rate was equal to the concentration of Cl, which was an intermediate, times the concentration of CHCl3. So we simply need to plug this into here, and in doing so, we get that the rate is going to be equal to K times the concentration of Cl2 to the 1/2 power times the concentration of CHCl3. And this is how we determine our rate law using our steady state approximation. And as we can see, if we go up to our overall initial equation, it contains Cl2 and CHCl3, which are expressed here in the rate law. So if you're given a particular mechanism and you look at the slow step and it has an intermediate in it, you have to employ this steady state approximation in order to try to determine what the overall rate expression is, or the overall rate law for this mechanism.